Recording guy. All good, recording guy? He says yes. Right, I'm going to keep you awake this afternoon. I want to go off the reservation. So if you feel like taking me off the reservation at any point in time, just chuck your hand up and we'll go off the reservation. So my name's Chris Auld. I changed jobs recently, so I'm the new DX lead for New Zealand. And I kind of like tinkering around with data science stuff. So do a bit of data science in the spare time, some Kaggle competitions, and a bit of automated sports gambling powered by a large low-wolf cluster under my desk at home. And we'll talk a bit about that shortly. So a bunch of the stuff today is kind of cribbed and pinched from various ML models that I've built. And I'm keen to sort of go through sort of the data science and analytics pipeline. I'm going to assume a little bit of data sciencey knowledge, that you kind of grok what it is to train a supervised machine learning model. Who's built a machine learning model before? Maybe a third. Okay, so we might go into a little bit more detail. So we'll talk a bit about and go through some approaches for data preparation, in particular feature engineering. All right, so feature engineering is the interesting part of doing data science. It's the art as opposed to the science. It's where you get to apply your industry knowledge, your domain expertise, to come up with crazy ideas and representations of the data that then feed to the machine learning model in the modeling stage, crunch through the numbers, validate that you have a good predictive model, hopefully understand what it means to overfit, what it means to not overfit and how to avoid it, and then operationalize. How do we take that model that we've built and actually go and deploy it in anger? Who knows where R was invented? Whereabouts? Yeah, over there. All right, so, and who can, I wish I had some prizes, who can tell me who it was invented by? And who else? Robert Gentleman, yeah? So, invented at Auckland Uni. It is the lingua franca for analytics computing. There are really two languages that you're going to use for data science. One is Python, one is R. The Python stuff tends to be focused a lot around things like deep learning. So most of the big deep learning libraries you're going to access using Python. Where R is really strong is the number of packages that you can get, right? If you want to do the modeling of honeybee swarms, there's an R package for that. And if you go to the CRAN repository, you can browse through a whole lot of different lists of domain areas where there are really good R packages. So the key with R is to really understand that it's about the packages that are available. The language itself and the runtime itself does leave a little bit to be desired. And we're going to talk a bit about what some of those limitations are and how we can work around this. This is really about taking an R-based pipeline and thinking about how can we work around some of those challenges. So those two key data science languages are Python and R. And R is growing in popularity. This is the IEEE Spectrum survey. So it really is growing in popularity. This is a slightly different pivot, looking at what are your classic analytics languages. SAS has for a long time been a pretty popular tool. It probably is waning. It certainly is. Who are there any SAS users? A few SAS users. Would that be fair? Yes, no? Use what you got experience in. Who's heard of big data? Yeah, and so James in the front row knows, but this is my little saying, and I parrot it all the time. If you haven't got a big data problem, but you think you've got a big data problem, you'll very quickly have a big data problem. This is called the parable of the visiting Hadoop salesperson. Big data is a right royal pain in the backside. So don't make yourself a big data problem if you don't have to. So let's think about what the data size spectrum looks like in R. And I sort of break it down into sort of four buckets. The first one is if your amount of data times the number of cores in your processor is less than your amount of RAM. That one's quite nice and easy to deal with. Anyone hazard a guess as to why I'm interested in the number of cores? Who are the R people? Who's done a bit of the R scale out stuff? So one of the problems with R, as we'll see shortly, is that it's single-threaded. And so you end up needing to run multiple R processors, and if you're a lazy person, like me, this allows you to basically just clone out all of your R processors and have a full copy of your data set in memory for each core. Next is if your data all fits in RAM. Next is if your data all fits on a single node. Still kind of small data. And then you've got your HDFS cluster. And frankly, folks, the vast majority of problems actually are achievable here. Because it's actually cheaper to go and buy 256 gigs of RAM than it is to try and dick around getting some of these other solutions set up. So by default, R will want to work with all of your data in RAM. And by default, R provides a single-threaded execution environment. So that presents us with challenges. As we have these really powerful machines, we can't take full advantage of them. When we go and start doing data preparation, in particular feature engineering, that can be quite an onerous process. So often we are processing all of the rows of data in our data set, and often we're processing all of the columns in our data set. So for example, I'll often end up with treatments where I'm taking all of the numeric columns in my data set, and I'm applying a dozen different treatments to them. So I'm taking numeric columns, I'll end up with 12 times the number of numeric columns produced as additional features. And you really want to, if you've got 100 million rows, you need to be able to spread that workload out, at the very least across the whole of your machine, if not across some sort of cluster. So a pattern to do that, and sort of the first one that you're likely to come across, is to use a library called ForEach. So ForEach is written by the guys at Revolution Analytics. Revolution Analytics got purchased by Microsoft to become Microsoft R Server. Typically involves some sort of either row-wise or column-wise partitioning of your data set, and then assign each of those partitions into a loop in the ForEach statement, and executing work against those partitions in parallel. And it probably feels kind of contrived to people who are used to doing multi-threaded programming, but it's a fairly manual process. The ForEach library relies on a set of parallel backends, and there are different parallel backends to provide different mechanisms for parallelizing the loops in ForEach. By default, R ships with a library called the Parallel library, which provides a thing called doParallel. doParallel comes in two flavors, doMC and doSNO. SNO, simple network of workstations. So doMC is the interesting one, and doMC is the reason I tend to prefer doing my data science on my Linux box than I do on my Windows box, because the Linux kernel supports process forking. Right, so what that lets me do is load my data set, stand up doMC. doMC forks the process to set up my parallel R processors, and it relies on shared memory for that initial data set and just saves deltas. Right, so it's a whole lot more RAM efficient, and that's pretty important. So I do tend to want to do my stuff on a Linux box for that reason. doSNO will work both on your local machine as well as on a cluster of machines, using either MPI or just plain old socket communications. With do snow and with the next one I'll talk about, you need to explicitly export the objects that you want to work with into the new processes. So as you stand up and spin up additional worker processes, you need to explicitly export data from one process, from your master process into the child processes. I don't use do snow much. Do MC I use a lot. Do snow I don't, because my preference for doing multi-node work with for each is to use the do Redis parallel backends. The do Redis parallel backend uses the Redis key value NoSQL database, effectively as a queuing mechanism for work distribution. It's got a bunch of nice characteristics, not the least of which it allows you to dynamically add and remove workers into your pool at any point in time. It does still require data movement over your network. So a pattern I find myself using quite often is to use a nested set of do Redis and do MC. So what I'll do is I'll have a for loop that runs on my head node, and that for loop effectively partitions up my data set and hands it out to the workers in my cluster. And then the workers in the cluster use do MC to further partition that workload to run across all the cores in each worker node. So again, a pattern that you'll find to be quite common. Who's going, holy shit, this is maybe a little deeper than I thought it was going to be? No, all good? Who's built an R cluster before? Who's done multi-machine, bit of multi-machine R? This is the sort of stuff you've... Yeah, so I mean, all of this is sort of converged over the years, right? So our MPI got rolled into, got end-of-lifed by snow and a few things like that. Okay, let's have a little look at a demo. Okay, is that reasonably visible? So I'm going to chuck all these scripts up afterwards. So let's start by going through and looking at some explicit parallelism. So I'll leave all the packages you've got to install at the top. So we're going to load up do MC, data table for each. This library called split stack shape I'm going to use later on to duplicate out my data, just to make a bigger data set. Numbers I'm going to use just to factorize primes and waste some time. And we'll load do Redis. So if we start with sort of an initial look at for each. So this is the call to for each, and there's a operator here which can be written as either do or do par. So do will execute each loop of the for each statement sequentially. Do par will execute it on the parallel back end. So if I go and run that out, and it's just going to go and find 10 times the next prime. I probably should have done a few less than 10 times. So you'll see that I'm pegging, I shouldn't be pegging 4 CPU cores. I don't know why it's pegging 4 CPU cores. Something's gone wrong. That's not a good start. Yeah, it was. Shouldn't have pegged all 4. Let's shorten it up a little bit. Run it again. You can only ever have a single parallel backend registered in your environment at any point in time. So if you want to run different sorts of parallel backends, you'll need to spin up additional R environments. It's taking a lot longer than it should. You will find yourself doing this a lot. The reason being is that when you're working in an interactive environment like RStudio and you spin up all these additional processes, RStudio doesn't actually know about the additional processes. So you can't use things like restarting your session and so forth inside RStudio. Okay, so that took 67 seconds. If we register a parallel backend to run on all 4 cores and execute it across all 4 cores. And what you need to remember is that this is a loop, right? And so every time it goes around the loop, it's going to hand it out to a new process. If you go around the loop really quickly with very small pieces of work, you end up paying quite a big overhead penalty, right, for the amount of work you actually get done. So you really want to try and chunk that work up, and think of, particularly as you go across the network, think of for each as a way of handing out work to worker processes, rather than, it's quite different to, parallelized for in C#, for example. Okay, so that was significantly faster. So, using do Redis. So, Redis is basically a NoSQL database. And one of the nice things about all of that stuff is that you can pick up something like Docker and run it pretty quickly. So literally all you do is you go apt-get install Docker. And I've already done it, but we'll do it anyway. And then I'm going to go Docker run. I pass through a port mapping, so I'm mapping port 6379 back out to my host machine, tell it to run the Redis container, and that'll stand up Redis on my machine. So basically this is now being used as a data broker for brokering these jobs out to multiple processes on my machine, but it could just as easily broker those jobs out to multiple processes across my cluster. So I'm going to register a different parallel backend. So I register do Redis. I give it a name that's going to be used to prefix the tables and containers. It's on localhost. A hot little tip, if you're working in with a Docker container, you've got to add this no delay equals false parameter. So that started my parallel backend. This next line is going to start up 2 workers. So these are worker processes running on my local machine. So if we jump over here, you'll see we've got these 2 additional worker processes. And then if I run that, so this one will fail. And so the reason this one's failed is that it says can't find function next prime. Right? The reason it can't find that function is I need to export objects out of my head node environment into those slave environments. So I do that by either using the .export parameter of for each or the .packages parameter. So in this case I'm going to use .packages, which means this will load that package into that environment. There's a whole lot more overhead when we start working with do Redis, right? Because it's not doing inter-process communication now. It's actually going and making a TCP call through the localhost network stack into Redis and back and forth to hand this work out. So the elapsed time will be significantly longer.
Should you make it up to 4 as well?
I can make it up to 4. I can make it up to as many as I want. I mean, typically what you'll... Yeah. I mean, I can do that. It'll still take longer because there's still that overhead, right? You'll typically be aiming for process to core affinity. So you're typically going to stand up the same number of worker processes as you've got cores in your machine. And you want lots of cores in your machine. Okay, one of the challenges with all of these parallel approaches is you've got all these worker processes off doing their work and no way of actually understanding what they're doing. And no one's really provided a particularly elegant solution to this yet. So the dirty hack that I use is I actually open a socket and then I run netcat on the terminal and I log against that socket and just basically watch the results coming out in the console. So I define this function called log, which just writes out to the socket, and then I'm creating a socket within my for each loop. Before I do that, I'm going to jump over here, and I'm going to go netcat listen on port 4000. So that's going to open the socket listener, and then I can go off and run that for each loop. Now, I think the problem here is there's some thread safety issues. But as a general, this is a pretty effective way of logging back from your worker processes as you go and update progress. So then putting it all together, so actually applying this to feature engineering in a data science scenario. Using doMC, loading up the housing data set from Kaggle. Anybody play on Kaggle? www.kaggle.com. Sort of like a machine learning competition website, but lots of interesting data sets and lots of good sample code. I'm going to dupe up a whole lot of extra rows. So I've now got 1.4 million rows in my data set. So what I'm doing here is I'm going to apply a treatment to all of the numeric columns in my data set. And that treatment's going to rank. So the housing data, let's do this. So this is basically a data set of house characteristics and with the target variable being the price that the house sold for. So what I'm going to do is I'm going to take all of those target characteristics and model worst house, best street, or in this case, worst house, best neighborhood. So I'm going to provide a rank for each numeric column by neighborhood and then turn that into a new feature. So rank each house by each factor within neighborhoods. And what I'll often do is I'll do a rank, I'll do a whole lot of other different treatments. I'll do a Gini coefficient or a Lefferstein number to try and come up with additional information to pass into the machine learning algorithm. So that pulls out just the numeric columns. Names of the numeric columns. Okay, and so a few little tricky bits here. So if you remember, I said you want to minimize the overheads here. So what I'm doing is I'm chunking my data up by effectively deciding I'm going to have a certain number of workers. I've got 4 workers, so I'm going to chunk my set of columns to be processed up into 4 chunks, or divisible by 4 chunks. I'm going to choose to pass in certain common columns, so I want these columns to remain in every loop. I'm going to pass in the ID so I can join things back later. I'm going to pass in the neighborhood because in each loop I want to be performing my operation grouped by neighborhood. A garbage collect before we fork. And then you'll see in here, so the outer, the for each here, that's going to represent my local worker process. Once I'm inside my local worker process, I get the set of columns that I'm going to be processing locally. And then I use the copy method against the data table to create a copy of that slice of memory. So remember, I started with a forked process, so all of the memory is being shared with the parent process, and then within that forked process I'm going to create a copy, right? And that's going to be my address space that I'm actually going to work in. Right? So what that means is I can be quite lazy. I can pass, I can pass around a reference to the whole data set because I've only got that in memory once. But once I'm in the child process, right, I need to have a copy of that so I have side effects interacting with each other across the workers. Use set key. So this is using the R library called data table. And you'll probably get pretty familiar with data table. Data table is effectively an in-memory database that you can use, and it's nice and fast. So the 2 common approaches to use data table or dplyr. There are dplyr interfaces that sit on top of data table to give you a nicer syntax to work with data table. Once I'm in my loop, I then have a simple for loop. Right, so inside my loop, I just want to be sequential, right? Because I'm in a worker process, affinitized to a core. So at that point, I'm just going to go and sequentially tap that core out and process the work for that core. I create a new piece of data called DT out, right, which is going to be that copy that I'd created earlier. I insert my newly generated columns into DT out, get rid of those 2 named columns that I passed into every local worker, and then return. And so what this piece of code gives you is a pattern for efficiently performing feature engineering on a column-wise basis across a really large set of columns. So that dealt with 1.4 million rows in 7.8 seconds elapsed time. And it created about 40 odd new columns. And again, I'll typically be doing, going from maybe a couple of hundred feature columns through to about 800 or 900 feature columns by the time my feature engineering process is finished. And if we go head results, so you'll see what we've now got is we've got newly generated columns, group dot rank dot, and the original feature name. The reason for the numbers is because I duplicated out my data set because the data set's only 2,000 rows. So I turned it into 1.4 million before we went and did this, otherwise it's a waste of time. I mean, unless if you're dealing with 2,000 rows, right? You know, you don't need to bother with any of this crap. But you know, once you start getting up over a few 100,000, you know, your feature engineering loop will really benefit from parallelization. Okay, so running an R cluster. Once you get into, you know, a few million to a few tens of millions of rows, you'll get pissed off with having a single machine really, really quickly. So, approaches for building a cluster. I went and got some X-Lease workstations off eBay, an InfiniBand switch, and put a cluster under my desk. And frankly, that is going to be the cheapest approach if you are using it a lot. The reason being is you want lots of RAM, and in the cloud, RAM is actually quite expensive. You know, so if you expect to be using this thing a whole lot, you're probably going to want to have a few machines of your own. You will still end up using the cloud. Once you start looking at the cloud, you want an easy way to stand up and tear down your cluster, right? Because you want your slave nodes to just basically be dumb nodes. Stand them up, have them do some work, tear them down again. And do Redis is really well suited to that, right? Because you can write yourself a Docker container, and I've got one that I'm probably going to send a pull request through for the next couple of days. You can stand up a Docker container that just runs do Redis, listens on your Redis cache in Azure, and then processes your work. Azure VMs are charged by the minute, and so it is not a bad approach to be able to stand something up, get your work done 5-10 minutes, turn them off. Because you're charged by the minute, you can turn on a whole lot more capacity, get stuff done in a shorter period of time. I don't typically run in a hybrid mode here. So I'm not typically running a cluster where I've got the machines on-prem plus machines in the cloud all reading from the same cache, just because the network overhead's too high, because we are pushing reasonably large data sets around here. So you can use the Azure Container Service. Positives there, it's nice and flexible. You may well have a container service deployment running already, so you can get away with using some spare capacity. The negatives are it is reasonably complex to set up, and if it's just your cluster, you've got a 3-machine overhead for masters and agents. If you're just running your own cluster, the pattern that I like is to use Azure Batch plus Batch Shipyard, and then do Redis. So basically it lets you use Azure Batch to stand up a batch pool, and then use Batch Shipyard, which provides an easy mechanism to deploy a Docker container across all of the nodes in your pool. Pretty simple to set up. The tooling's in Python, so if you want to run everything in R, you've got to have some mechanism to funk out to Python to kick things off. It feels a little contrived using Azure Batch, because strictly speaking, Azure Batch is in and of itself a work distribution mechanism. So it has its own way of divvying work out across a pool. And you're kind of circumventing that by using do Redis to go and do your work distribution for you. But what this does mean is you can stand up a pool of 3, 4, 5 nodes, run that. If you want to add additional capacity, stand up another pool with as many nodes as you want. As long as it goes and talks to the same do Redis endpoint, it's going to continue to pick up work off that cluster. So that's basically parallelism during feature engineering. You know, and that really becomes important once you're into those sort of few million rows. Even under a few million rows, once you come to modeling, you're probably going to want to have some sort of parallelism as well. So this is basically taking my features, giving them to a machine learning algorithm, and having that go and train on the data. If you're running just a single node, most of the more sophisticated ML libraries are going to have implicit parallelism in them. If you use XGBoost, it's parallelized. If you use a parallel version of a range of other packages, Arborist, GVMs, parallelized. So there's a couple of random forest options up there as well. You can also do explicit parallelism, again using for each on your local node. So if you're building random forests, you can easily parallelize building random forests. You just need to be conscious that in order to do your own explicit parallelism, i.e. using something like for each, your training model needs to be an embarrassingly parallelizable operation. And what that means is there needs to be no requirement to have communication between those parallel execution processes while the process is occurring. So the reason random forest is great, because random forest is just a pure bagged tree model, right? So go and generate a whole shit ton of trees, bring them all together, vote or bag out, average the results, piece of cake. So that is, it's really, really easy to scale that out in a simple fashion. Compare that with, say, gradient boosted machines or deep learning, where your parallel tasks need to understand the result of each previous tree or each previous epoch as you go through that training process. You don't want to try and roll that stuff yourself by hand. You know, again, if you are, for the vast majority of scenarios, if I was to say, you know, go use this machine learning algorithm, it's to go use XGBoost. Anyone use XGBoost already? One person. Okay. How many used R? Great. So there's at least a half dozen people who can go and take something away straight away, which is, you know, go have a play with XGBoost. So it's a boosting machine, tree-based model. It wins all the Kaggle competitions, right? So, you know, for the vast majority of sort of non-image, you know, non-complex data sets, it works pretty well. So for multi-node parallelism, so again, if you've got an embarrassingly parallelizable task, building a random forest, you can go and do that explicitly. Otherwise, the place where you're most likely to want to scale out across a cluster is when you're doing things like hyperparameter optimization or cross-validation. So cross-validation is a way of assessing model fitness, which doesn't use a holdout test set. So if you think about training a supervised machine learning model, what you'll typically do is you'll say, I've got 1 million rows of labeled data. I'll keep 200,000 rows aside, I'll train on 800,000, and then I'll test how well my model performs on 200,000. The problem with that approach is you've just thrown away 20% of your data, right, in terms of actually building your model. So what cross-validation does is it says instead we'll take 200,000 out, train on 800,000. Then we'll take another 200,000 out and train on the other 800,000. We'll do that 5 times. Right? That's called 5-fold cross-validation. 10-fold cross-validation would be 1 million rows, take 100,000 out at a time. It's a really nice way to use all of your data. That's the upside. The downside is instead of building one model, you're building 5 models. Or instead of building one model, you're building 10 models. But all of those models can be built independently, so it sits well with actually pushing that work out across a cluster. So that's cross-validation. Right? So cross-validation is really useful to be running any time you're assessing your model fitness. Hyperparameter optimization is basically a brute forcing operation to determine what parameters to your machine learning model work best. You know, so if we think about something like a gradient boosted machine, which is a tree-based model, how deep do we make the trees? What shrinkage level do we apply against the algorithm? So, you know, what sort of regularization do we put onto the algorithm? And then you go and combine these two. So you're going to do cross-validation, plus you're going to do a grid search across a range of hyperparameters. So, you know, you go from, okay, I was building one model to now I'm building 10 models. And I'm building 10 models for every hyperparameter path. And my hyperparameter grid is 4 by 4 by 4 by 4. you start to end up having to do a whole lot of work. You know, and if your base model takes a couple of hours to train on a single node, you're just not going to be able to do that without having a cluster. There are some packages that provide sort of existing support to use a parallel backend, but for the most part, sort of the use of parallel backends by any of the sort of the modeling algorithms themselves is pretty limited. Most of them will shell out to C++ to do that. You can use an external multi-node solution. So a good example there would be something like H2O. So H2O is a Java-based machine learning framework, provides GBM, GLM, an okay-ish deep learning implementation, and a couple of others. But you know, if I were to say, okay, XGBoost is pretty good, and if you want an easy way to do multi-node training, i.e. where we need to span a single model training across multiple nodes, then H2O is probably the easiest way to get to there. XGBoost can be distributed, but you're going to be mucking around setting up Yarn or Spark or something like that. You know, so Spark, Yarn, you don't necessarily have to have big data to justify going and setting up those tools, because there will be situations where you want to scale the work out across multiple nodes. And then something like Azure Batch. So Azure Batch plus Docker, that batch shipyard's got pretty good support for running all of the major deep learning toolkits. So TensorFlow from Google, Caffe, Tiano, CNTK from Microsoft. They renamed CNTK yesterday, so we're just going to call it CNTK today. And I will put all this stuff up on GitHub straight after this so that you can all go and pull the code. You know, all the sort of, with all the demos, the complex examples at the end are actually pulled out of real stuff that I do, just with a different data set. Okay, so parallelism during modeling. Let's start by loading a couple of libraries. So random forest is just a super simple random forest algorithm. It is not parallelized. Arborist is a parallelized random forest. We'll load up that same data set. And I'll just do a quick and dirty approach to get rid of the NAs in that. And then let's build a random forest and a arborist model, each with 300 trees. And what you'll see is, as it builds the random forest, it's pegging one of my CPUs. And then once it changes to building the arborist model, you'll see that it actually goes and pegs out all the CPUs, because the arborist model supports running across multiple cores straight away. It's a little like watching paint dry. So one of the things you get really good at when you start playing machine learning is you have these sort of scripts that you kick stuff off and then bugger off for a bike ride. Right? So I mean, I have a 4-node cluster that sits under my desk that trains from about 1 a.m. to about 6 a.m. It all gets wake on LAN powered up. Because I buy spot price power because it's 6 kilowatts. So you'll see it's significantly faster, you know, and over an order of magnitude faster to run using the more optimized algorithm. So Arborist is a faster algorithm, you know, regardless, even if you lock it down to a single core. Okay. There's a library called, well, there's a couple of libraries that you'll probably want to have a bit of a look at if you're going to start doing a whole bunch of machine learning in R. One is called Carrot, one is called MLR. They are competitors to the extent that you have competitors in the space of sort of free open source tools. But they're basically meta packages to build machine learning workflows. So they provide mechanisms that wrap all of the various machine learning algorithms and provide things like cross-validation, model evaluation, hyperparameter search, and so forth. So in this case, we're going to use Carrot, and Carrot naturally supports, well, by default supports the use of a parallel backend, so we'll also load Parallel. And again, Parallel ships with R. If it's running on Linux, it's going to run as doMC with process forking. If it's running on Windows, it's going to go and run do Snow and use socket communication to communicate between the worker processes. And you will, Carrot does it, but it will need to export the appropriate objects out into the child processes. Okay, so we are going to set up a gradient boosted machine. And we're going to do, why has it not got the number of folds? We're going to do a repeated cross-validation. We're going to run multiple pass cross-validations, run it 3 times. So again, what that gives us is we do our multi-fold cross-validation, and then we change where we cut the fold points and run it again. We change where we cut the fold points and run it again. Right? What we're trying to do here is to make sure we don't end up in a situation where we kid ourselves that we've got a model that's good when all we've done is overfit to the data set. So we're going to use cross-validation to evaluate our models, and then we're going to use a grid search to go and evaluate the hyperparameters. So we're going to look at this, and we are going to do a run where we build 2 trees, 5 trees, 7 trees, 2 nodes deep, 5 layers deep, 7 layers deep, 9 layers deep. We're then going to evaluate the model at 100, 200, 300 trees. Right, so a GBM is building lots and lots and lots of decision trees and aggregating the results of them together. Nice thing about Carrot is it understands that in order to test this hyperparameter, it doesn't need to build 3 models. It needs to build 1 model of 300 trees, and then go and evaluate it at 300 trees, go and evaluate it at 200 trees, go and evaluate it at 100 trees. So it does understand, and so that's a nice characteristic, which is, you know, a benefit if you were going to do this yourself. We're also going to add in shrinkage, so effectively the learning rate. We're going to try it at 0.01, 0.1, and 0.3. And we are not going to add the minimum number of observations in a leaf node to our grid search. You know, and this really is, this is brute force, folks. So, I mean, we are literally taking all of those and expanding that grid out. And we'll register 4 workers. So if we go get do par workers, so get do par workers is useful as a way to determine how many worker processes are going to be spun up. Use it a lot when you're deciding how you're going to chunk up work. And if we go ahead and run that, and this should peg out my CPU pretty well.
Out of curiosity, Chris,
Yeah.
what kind of data do you do machine learning
Sports gambling.
Make any money?
Not prepared to comment.
Nice shirt you're wearing.
It's a very nice shirt, handmade. Do you want the shirt off my back, mate? So that's pegged this out pretty well. You'll see that some of the work's starting to finish now. You get really used to watching these charts and sort of reverse engineering what you think's going on under the hood in terms of stuff finishing. You know, and this is running on my local laptop. I mean, this is a rather anemic machine. We'll log into something else shortly. Okay, so what that's done is it's done its grid search. It's found out that the best model was built with 200 trees, 7 levels deep, learning rate of 0.1, and again, ignore that last one because we didn't grid search on it. And then I can also output all of the different models that we built, right? So we went and built 36 different models there. So again, if you've got a model that takes 2 hours to train for one model, and you do it 36 times, that's most of the week, right? So being able to spread this stuff out across a cluster is really, really important. You know, and you know, to give you an idea, our data set's about 9 million rows, and you know, it takes about 4 hours to train on a 4-node, 64-core cluster. So it's reasonably onerous. Okay, last thing I thought I'd show you is this thing called Batch Shipyard. So Batch Shipyard is a little Python library. And you just go get it from GitHub. And basically what it does is it provide an easy way to run Dockerized workloads on Azure Batch. Anybody play with Azure Batch already? So Azure Batch is what was the green button, guys. All right? And Azure Batch is designed as an easy way to distribute workload out across often very, very large numbers of machines running in Azure. There's no additional charge for using Azure Batch. All you pay for are the virtual machines that you're running underneath. So this makes it easy to stand up a cluster and then push out a Docker container running the tool of your choice into that pool of machines and have it execute for you. I am building an appropriate recipe for Batch Shipyard for R, but it's not finished yet. So when it's finished, I'll send a pull request into Batch Shipyard and go and twist some arms and hope that they take it. So instead, what I'll show you at the moment is how this works running CNTK, which is the Computational Network Toolkit, which is Microsoft's deep learning toolkit. Anybody play with that yet? TensorFlow, Caffe, Tiano, MXNet. So we provide it with the credentials. So here's the credentials it's going to use to get to my batch account and my storage account. We pass in a key. We then specify the pool that we want. So I'm going to have a pool called CNTK CPU multinode. It's going to run D1 V2s. I'm going to have 3 nodes. I'm going to use Ubuntu Server 1604 long-term support. I specify the SSH tunnels that are going to be used for inter-node communications. And then what I'm going to do is I'll jump over here and run Batch Shipyard, add pool. I wonder if I can see if I can make this text a bit bigger for you guys. Come on, make text bigger. No, not going to get it done. So basically, I run add pool. It's going to go and talk to Azure Batch. It's going to stand up a pool of 3 of those machines. And I did that earlier because it takes 3 or 4 minutes. Then we go and define jobs. So the job's named. We specify that it's either going to be a standard batch job or a multi-instance batch job. So a multi-instance batch job is basically required if you have that situation where the nodes in your pool need to communicate with each other as part of that piece of work. All right? So if the actual piece of work runs across multiple nodes, you need to configure it as a multi-node job. I give it a Docker image, and it's going to go and fetch that Docker container from Docker Hub. I specify a shared data volume, and so this image actually defines shared storage using Gluster. And then I pass in the commands that I want to be executed once that container stands up. And so this command is just going to use npi run to kick off CNTK. And if I jump back in here and execute the job, and then I'll pipe the job results back out to my local console. So that's now going to go and push that job out across the entire pool of machines. So my pool of machines is over here. So I've got 3 machines running. It's gone to those 3 machines, pushed out the Docker container, started the Docker container, run npi run, which in turn has executed that CNTK job. That job's run across the cluster with inter-node communication occurring, and then it's written the results back out to that shared Gluster volume. But what I'd probably do is write those results out to blob storage in most cases. So you'll see it's basically run a deep learning model out across that cluster. If you've got access to the new N-series VMs, which are the new GPU VMs, they're going to be what you want to run your deep learning models with. I haven't yet, unfortunately. All right, who's still with us? Not too painful? Is this what you're expecting? Shit, right, okay. So you want lots of RAM, right? Because ideally you want your data set to fit in RAM, because as soon as your data set doesn't fit in RAM, it becomes a real pain in the ass. So if your data set doesn't fit in RAM, you need to have a mechanism whereby you can actually read the data off disk, stream the data through whichever algorithms or libraries you're using, and then write that data back out to disk. There are a couple of sort of freebie libraries out there, one called Big Memory, one called FF, that can do that for you. Another approach is to use dplyr at the top of a relational database. So that works as well, but it's very, very slow, like really slow. And the biggest problem with this is it tends to present, the biggest challenges tend to present themselves once you start getting into modeling territory. All right? If you are modeling in R, you're pretty much screwed without having enough RAM to hold your data. Yeah. So that Python's the other sort of common one. Most of them want you to have the stuff in RAM, right? The common pattern once you don't have stuff in RAM is to start spreading it out across a cluster. The common languages, the benefit of R is just all of those libraries. Because you say, oh, I want to You know, I've got groups of items that I want to compare and I want a measure of inequality. Okay, you go look up inequality, the inequality package in R, and there's like, you know, 40 different approaches for modeling inequality, right, which is great for feature engineering. R does it better. R does it better because most of the stats departments around the world build stuff in R, right? Deep learning tends to be approached with Python because most of the computer science departments around the world are building their stuff in Python, right? Because the sort of the statsy stuff's usually coming out of the math and stat department, and the deep learning stuff's coming out of the comp sci department, and pretty much all of the stuff comes out of academia, right? You know, and the other thing, if you start playing with the machine learning stuff, you will read a lot of academic papers. Like I haven't read an academic paper for like 10 years, and then I got a bloody Kindle full of academic papers. And they're really good. Like, so the journal that's worth keeping an eye on is the Journal of Statistical Soft, JStatSoft. So most R packages for the academic to get their publication credit, they need to publish a paper. So usually when they're building a package, they're going to publish that paper in JStatSoft. And we're running really long, which is bad. So multi-node. So multi-node, H2O is really good, but quite limited support for data wrangling, so no good for feature engineering. Spark R, Spark SQL, so doing this stuff on top of a Spark cluster, that's probably the sort of gold standard approach used by the major players at the moment. And then sort of an enterprise land, RevoScale-R, which is the Revolution Analytics stuff that Microsoft purchased and turned into Microsoft R Server, provides a really nice way of external memory feature engineering and external memory modeling. So we've run super long. I'm not going to dive into Microsoft R Server too much, except to say that it provides you with that mechanism for external memory storage, be it in relational database, SQL Server, Teradata, HDFS, Spark, HD Insight, and then an ability to stream that through a range of machine learning algorithms they've got, and they have mechanisms called a data step, which allows you to perform transformations in your feature engineering loop. R Server is available on HD Insight Premium, so 2 cents per core per hour to light that up. It's a pretty easy way to get hold of it. The other place you're likely to play with Microsoft R Server is if you're using SQL Server. R Services for SQL provides this stuff with the execution occurring in SQL, but you can actually span that execution out across multiple nodes. So pretty simple to stand up a cluster with R Server. It can get quite expensive quite quickly, right? You know, so the common pattern with HD Insight is, you know, I've got a huge amount of data and therefore I need to store it in HD Insight. I'm going to run my cluster all the time. If you're using HD Insight for compute power, then what you're probably going to want to be doing is stand up the cluster, load the cluster, process your work, tear the cluster down. So running Spark plus Spark R will let you use things like Spark SQL to do sort of SQL-like data transformation. I won't do this demo. I will publish this code. In order to execute this piece of code, you need to have the RevoScale-R libraries. The way to get the RevoScale-R libraries is to download and install the Microsoft R client. So the R client has all of the RevoScale-R libraries in it, and they will run in that external memory mode. But before they do that, they will check how much memory you've got, and if you try and work with data that's larger than the amount of memory, it'll fail on you, which is just a licensing constraint. So I will publish that code. Productionizing machine learning models. I sat on a conference call with someone a few weeks ago, and they said I would never use R in production. Well, you know, that might have been an okay approach to take when all we did was fit linear regression models. But now that we build complex tree models, you just can't get away with trying to port all that shit over to some other programming language. You need to have a mechanism to run your R pipeline, because you're probably doing a whole shit ton of feature engineering in R, and then your resulting machine learning model is probably some, you know, ginormous 3,000 tree ensemble that you really don't want to back out and for 6 minutes shit turn into, you know, turn into bloody, you know, C or anything like that. SQL Server R services is great. It's great even if you're not necessarily using the RevoScale R stuff, right? So you can use SQL Server R services to call out to R code from within SQL Server. Azure ML. So Azure ML lets you really easily publish R up and hang it behind a web service. So you're working in R. There's an R library called Azure ML. Take the space out, load that with library, and load it with library, log into your workspace in Azure ML, run the publish web service function, and that pushes your R function, this one here, scoring FN, or whatever named R function you want, up into Azure ML, and then you can call it hanging behind a web service. So if you've got complex R pipelines with R-based feature engineering, you can push it up, run in the cloud. It's quite expensive. So if you're doing this at really, really big scale, you're probably going to want to go and roll it yourself. Folks, sorry if I ran you long. Questions, queries, problems, thoughts, commentary. Holy smoke. Useful content?
Is there a canonical entry point for R in a book or a place?
Entry point for R, yeah. So I would get the easier of the two Hasty and Tibrashani books out of the Use R series from, I think it's Wiley. So Hasty, Hastie, and Tibrashani, and I would go and hang out in Kaggle. The best place to learn machine learning is to go to Kaggle. Sorry, Coatsy, how are you, fella? Sorry, mate. I'll get out of your hair. I'll be outside. Thanks.